Okay. So no, I see the attendance very poor by the way. Only 11 guys have joined. Uh, so if you have questions from the last class, which I did on something on second quantization, very, very elementary because these are supposed to have been taught already in quantum field theory. So I gave my way of looking at the second quantization because you start from the wave function in quantum mechanics, and so because your aim is to deal with many particle system, you replace your wave function by the fields. And then, of course, uh, you can expand the fields in terms of creation and annihilation operators. And this creation and annihilation operators are going to operate on a occupation basis. And the occupation basis, you can represent the n particle state by mm, yeah by sorry the you can represent the cat where you're going to operate by creation and annihilation operator. These cats they are supposed to be n particle state, and in the n particle cat you take the notation as occupancy and the maybe wave vector index, and the creation and annihilation operators are going to operate on that. And if they are fermions, they will have anti-commutation relation for this creation and annihilation operator. And of course, for the boson, you have commutation. You can prove that. So I gave a glimpse of whatever one is supposed to be doing in the second quantized notation. Yes. So if there are problems, I can address. If there are none, I can proceed. So tell me what I should do. Yes. Now, if anybody has any question anywhere, I mean, whatever I am doing, I can clarify. There's no problem absolutely. Yeah. But this one has to learn. There is no other way. Anybody wants to say anything? No? So I can go over to the slides. Let's see. Okay, here I go. So, whatever we did last lecture, they are already there. Just 1 minute. So one can the one differences I said here is usually in many particle theory, whenever we go for field expansion, you can have something like complete setup expansion, the way we do it in quantum mechanics, and this coefficient which we call coefficient in quantum mechanics. This becomes now an operator, and this becomes the basis. In typical quantum field theory, this becomes a linear combination of this part and the Dagger part also. So in many-body theory, we don't do. I mean, if you want, one can do also. There is no problem, absolutely. But for simplicity, one can retain psi as this and psi Dagger as this. Okay, and then of course, using the orthonormality of this basis sets, you can have the anti-commutation relation if they are fermion operators. Okay, so that's a little different. And then one can write down any operator. Like here I tried kinetic energy operator. And I haven't explicitly written kinetic energy operator because I'll do it. Just wait for some time whenever I go to discussion on solids. And this precisely looks like sum over this ij, and I and j are basically the basis set, phi I star and phi j. This is the basis set. This is a bra and this is a cat. And then the kinetic energy operator is sandwich here. So this is basically the matrix element of the kinetic energy operator in this ij basis. And then of course you have Ci Dagger Cj. These are basically second quantized creation and annihilation operators. So your kinetic energy looks very simple. And any one body operator is going to be something like this. But if you come to two body operator is interaction between two particles or two fermions, let's say. Then, because this is going to depend on two space-time points, so you'll have field operators in the right-hand side and field creation operator in the left side, sandwiched by this potential energy operator, and then integrate out all coordinates. And this is going to be something like this: your potential energy operator, the matrix element with respect to IJKL basis, and then, of course, 2 Dagger and 2 1 Dagger. So there are 4 fermion operators. So your potential energy looks involved. I'll tell you why this is not very easy to handle. And then you have all this sum with a factor of half. I said your double counting is avoided because I can't put the particle in the same site or same state. Okay. There are many operators. I can think of charge density operator. I can think of current operator. There's so many. So now let me try looking at a piece of solid. Can I write down a Hamiltonian for a solid? If you start writing down a Hamiltonian for a solid can be a metal, let's say, or a piece of copper metal or aluminum metal, any metal. Then you will have at least 2 degrees of freedom. That is, you can have a pure electronic part, pure bosonic part. This bosonic part is basically the ionic part, and then the interaction between these two. Okay. Now, electronic part, see, just the way if you look at a solid has some periodic arrangement of atoms. Atom will have a core and it will have valence electron. So the core is something like a boson ionic core. And your electrons are basically fermions. So this is the electronic Hamiltonian, and this is a bosonic ionic Hamiltonian, and this is the interaction between both. So let me try explaining you a bit, because these are all many body. So your electronic part has kinetic energy for each electron, identical particles. So your aim is same for all. And I put index I, sum. So this is n electrons kinetic energy. And now this is a two-body Coulomb potential. just two body. I'm not going beyond two body. So electron sitting at Ri and Rj, they will have interaction 1 by Ri minus Rj. And I is not equal to j, because that's why I put a factor of half here. Because this is going to shoot off. And that is not going to be allowed because they're fermions. So you have 1 by R potential, and the potential is repulsive because if you take two electrons, they will have Coulomb repulsion. This is Coulomb repulsion 1 by R. And the charges of each electron, that's EE, is square. And there's a sum, by the way. I is not equal to J. So let's say, suppose you fix I equal to 1. Then J can be 2, 3, 4, 5, up to N. So electron 1 will have a Coulomb potential with 2, with 3, with 4, with 5, 6, up to N electrons. Now then I equal to 2. Electron 2 will have a Coulomb potential with 1. It will have the Coulomb potential with 3, 4, 5. So it will go on. So if you think of, if you break this sum, this will look massively complicated. Okay, so this is not just only two electrons. Because I have n electron problem, the kinetic energy you can just sum it. But here, once you evaluate this sum, it will have a large number of terms, and it is going to be a complete mess. This is what it is. I mean, you can't do anything. So because there are a large number of electrons, I have put here a factor called screening. I'm calling it as a screening, but because this will have a singularity 1 by R, so Ri approaches to Rj, it is very large. So in order to handle mathematically, because I don't know whether you have handled this mathematically, if you do quantum mechanical scattering, then you have to do this integral, which involves 1 by R. And it is going to be troublesome because it is going to put you in trouble because of this singularity. So what happens is, in order to handle this, you put a factor e to the power minus mu r. Okay, and one can put it mathematically without knowing screening, but then it has a reality that if you have an n particle problem, of course there will be screening. Because let's say, suppose if you put n particle and fix up, if I ask a question, is particle 1, which is going to interact with particle 1000, the 1000 number of particle will be sitting somewhere at a distance, and that fellow cannot see electron 1 properly because there will be large number of intervening electrons. So your electron 1 will get screened out by others, and the 1000th electron may not be able to see electron 1 properly. So the interaction between these two is going to be screened. Do you understand what I said? If you have only two electrons, then there's a bare interaction. Electron 1 is going to interact with 2, or 2 is going to interact with 1. There is no problem. But if you have a large number of electrons, Avogadro's number, and if I take electron 1 and electron 1000th, then there will be a large number of electrons in between. So they're going to screen. So the 1 and 1000th, their interaction won't be just 1 by R. Because it will be screened by this kind of factor. And your mu is going to be the parameter related to screening. So we will see this, but I don't know whether you understand what exactly I'm saying. So your Coulomb repulsion for n particle problem cannot be just bare. It can be effective because of screening. Okay. Uh, so for ionic interaction, your ion, they can have a interaction again similar to this half e square. And by the way, for electron, I have just put to differentiate, I have put a sum here, and here I have put an integral. This can also be a sum, there's no problem. And this is again 1 by x minus x prime e to the power mu minus mu x minus x prime. And of course, this density is just 1. Here also there's the density, which I have taken as 1. So you think of this is also 1. And x are the coordinates of the ions, and r are the coordinates of the electrons. So just to distinguish, I have written in this form. And of course, both are ion-ion repulsion is also repulsive. This is also repulsive. Okay, but if you look at ion electron potential, then of course it is attractive. So you can have again 1 by r potential. Here sum and integral both I have kept, because one is for electron and another is for ions. And this is also going to get screened. So this is the typical Hamiltonian, which looks massively complicated. Because why massively complicated? Because it has 2 degrees of freedom, and these are all interactions, 2 body interactions, and there is because of this sum and integral or this sum, it will become very complicated. So you just can't handle this. Okay, so now the way I was trying to tell you about a piece of solid, and I came across the notion of free electron gas by throwing out a lot of things. This is what precisely I'm going to do here also. Okay, because the ions are heavy, the lifetime is very slow. So that is going to simplify the problem. So you can go for many approximations so that things could be clearer. Okay. So,
Sir,
any
uh,
question anybody has? Yes.
sir, how the screening term is helpful in
Hmm.
hello?
Go ahead. Go ahead. Go
Yes.
ahead.
So how the
Hmm.
screening term is helpful uh, in re- removing the singularity?
Okay, because see, you tried doing a integral 1 by x to the power something, let's say, square or cube or whatever, from just minus 1 to 1. You'll have problem. Can you do 1 by x square integral from minus 1 to 1?
No, sir. It will come in 1/0, I think.
So what you can do is you can put a factor called e to the power minus x, or let's say don't take that. I'll tell you something else. Suppose you just do sine x integral from 0 to infinity. Can you do sine x integral from 0 to infinity? Hmm. Anybody in your class who
So it
can
will
do
improper.
sine?
Yes.
Huh.
So I
Follow.
think 0 to infinity sin x will be an improper integral.
Why?
So because the value that we get is not finite, I think.
Hmm. No, it is not finite. You don't know what to do, because see, it is something like ill-defined. Because let's say sine function is the periodic function. If I give you 0, it is fine. But infinity doesn't have meaning. Sine infinity or cos infinity, it doesn't have any meaning. But suppose some such thing comes out, and in Coulomb integral, this is going to come. You can't help it. So what one can do is, because you don't get a meaning out of that, and you want to give a proper meaning to it, so you multiply factor e to the power minus mu x or mu r. And this e to the power minus mu r, because this is a decaying function, it is going to give a proper meaning to the integral. And you can do the integral, but mu is going to remain. And then at the end, once you perform the integral, you take the limit mu tends to 0, if it is just a mathematical stuff. And then you will get an answer. So I'm saying in many cases, if you have singularities, because infinities are going to come, or you may not be able to do such integral, or it may not give you a proper meaning. Then in many cases, this exponentially decaying function is going to help you. It will allow you to do the integral, because it is going to give you a meaning. And at the end, after you do the integral, mu is going to be a part of that answer. And take mu tends to 0. So you'll get the correct feature. Have you done the scattering, your Coulomb potential scattering? So when you do Fourier transform and all that, or even if your mathematical physics class, Fourier transform, can you do a Fourier transform of 1 by r? Now, if you do this, you are going to have problems. I don't know whether you may not have done properly, I think. You do properly, just take a Fourier transform of 1 by r. So you are going to have this problem. Yes, so that is purely mathematics. But now I am telling you physics. It is not just math. This mu is, I don't need to put it to 0, because this is going to be a physical parameter in the system. You can estimate this. Do you understand whatever I said?
Yes, sir.
Okay. Yeah. Any other question? And now you realize the two-body potential, Coulomb potential, could make things extremely worse if it is a n-particle problem. समझ में आ रही है ना? Because
Sir,
if I open this sum, it will be just horrible. Yeah, हाँ बोलो.
sir, ये mu क्या होता है?
Mu is basically, देखो ये r है, so this is inverse of r, so it will be something like a wave vector. Yeah.
Okay, sir.
Yeah, inverse of length. So because this becomes dimensionless. Yes. And now it is just a parameter. So how kuch puchna hai? See, I'll spend little time on this, because these things are going to be very essential and you should be knowing all this. Born open higher approximation kabhi padhe ho quantum mechanics mein? Because if you have many degrees of freedom, how to eliminate depending on the dynamics. Yeah, okay. So let me just move and I'll tell you a few things. So just the way I have done for electron gas, I started with ions, electrons, and then, so this is a similar thing. Okay, so in principle, all the above Hamiltonian will diverge in thermodynamic limits, because if you take this, they are all going to diverge. So we have to make a meaningful stuff out of it. And about mu, I said mu is going to give you a meaning for the time being, because screening I am going to discuss after this chapter. So don't worry. So consider only the dynamics of electron as compared to others and compute ground state properties per particle. That's the aim. And to do this, we have to use the mass of ion very large as compared to electrons, and the dynamics of ions are very slow as compared to electrons. So I have to treat the ionic degrees of freedom purely classically. Okay, that's what we are going to do. So at bosonic Hamiltonian, I just do this integral. This is one because these are densities, and just take x minus x prime equal to z. So these are densities, meaning n by b, n by b, n by b square. So I can get it something like this. And if you do this integral, you're going to get you something like 4 pi by. Okay, I'm sorry. Just 1 minute. Okay. So it is audible properly now.
Yes, sir.
Okay. Okay, so can you hear me properly?
Yes, sir.
Yes, sir.
Okay. Okay, so you can do this integral because I just take classical, treat them classically. So these densities are number by volume, and half e square dq x, this is dq z, e to the power mu z by z. Okay, so the result is this. And of course, this is going to be infinity if you take mu tends to 0. So looks like unphysical stuff if I take the limit, meaning it is going to be infinity. So as boson electron, also I can do the integral for bosonic part. Okay, so this is again going to be something like this. So if you look at these two term, this is half p square n square by v, 4 pi by mu square. This is e square minus e square n square by v, 4 pi by mu square. So if you add this one and this one, it's going to be something like this. Okay, so just take it because there's a beautiful cancellation which I'm going to show. Okay, now your H boson and H electron boson, I can look at that as something like minus half e square n square by v, 4 pi by mu square. Okay, now if you look at electronic part, because we are interested in this, we have this. So first I'll simplify a bit about my kinetic term, and then I'll handle this. Okay, we'll come to this again. So the way I was telling you, your kinetic energy term can be written as some ij and the matrix element of kinetic energy operator with respect to ij basis, and then ci dagger cj. This is what I have written earlier. Now we are going to compute this because in a free electron gas, suppose if I don't have this, then this problem is exactly solvable in a box. And the state we have used is plane waves, 1 by root b e to the power ik dot r. And I can put a spin wave function also, because the spin wave function is just a tensor product with respect to this, because the orbital part and there's a spin part, they don't talk to each other. So there's a tensor product of, and this is going to be silent because your Hamiltonian doesn't have spin unless I come back to electrons. Okay, so these are already I have written down. Now the matrix element of kinetic energy operator, we can calculate it now. In my kinetic energy Hamiltonian, I have ITJ, then Ci dagger Cj, and then the sum over Ij. So your I and J, I can take K1, K2 basis, because here you already know the basis. Basis, I said it's a plane wave here. So your K1 is basically psi K1 sigma 1. So 1 by root B, some such thing with chi sigma 1. So we can do this. And kinetic energy operator is minus h cross square del square by 2sn. So h cross square by 2sn I can pull out 1 by v dq bar this spin wave function because of the dagger, and then minus del square of this, and this can operate on this basis states, and it is going to pull out a factor of ik2 square. Chi sigma 1 dagger chi sigma 2 is just sigma 1 delta sigma 1 2, and then 1 by v after operating on this, then this basis can be some. This is again a delta function delta k1 k2. So your k1 will be k2 on this k2 k1 equal to k2 equal to k. I can put a k. So this is h cross square k square by 2sm and two delta function sigma 1 sigma 2 and k1 k2. So your matrix element of kinetic energy operator in the plane wave basis is just this, with of course the delta function, because there's a sum over k1 k2 and sigma 1 sigma 2, because this is I and this is j and both are summed. So your k1 k2 sigma 1 sigma 2 are summed. So your sigma 2 sum can be taken out from this, and k2 sum will be taken out by this delta function. So you'll have k sigma or k1 sigma 1, and then you see k dagger ck or ck sigma dagger ck sigma, it is going to come out to be. So your kinetic energy operator, which is supposed to be ITJ, sum over IJ, ITJ, and then Ci dagger Cj. Now that you replace it by sum over K1 sigma 1, K2 sigma 2, and then this matrix element, this, and then C K1 sigma 1 dagger, C K2 sigma 2. And you put this value in place of matrix element, and then two sums k2 and sigma 2 sum will be thrown away by this, and you'll have only epsilon k ck sigma dagger ck sigma. Now, so I have put the kinetic energy term in terms of pure second quantized Hamiltonian in terms of creation and annihilation operator. Do you understand this? Whatever I have done. You go here. Say for example. Okay. Sorry. You go to this place. So your psi dagger is equal to phi I Ci. Okay. And now we come back to this place. So I am saying you, in place of I, you write down K1 sigma 1. And here in the sum also K1 sigma 1. And J K2 sigma 2. And C K1 sigma 1 dagger, C K2 sigma 2. And then your matrix element, this, if you calculate it, it is going to be h cross square k square by 2ism, delta K1 K2, and delta sigma 1 sigma 2. So here, you out of 4 sum, K1 sigma 1, K2 sigma 2. K2 sigma 2 you can take out by this 2 delta function. Your K1 equal to K2 and sigma 1 equal to sigma 2. So sigma 2, in place of sigma 2, you write down sigma 1. In place of K2, you write down K1. So you will have only two sum K1 sigma 1, H cross square K1 square by twice n, C K1 sigma 1 dagger, C K1 sigma 1. So now you K1 and sigma 1, because these are dummy variables, you can just put it K and sigma. That's what I have done here. Yeah, so that's precisely. So see, your single particle or the kinetic energy Hamiltonian looks like the single particle energy eigenvalue becomes the matrix element of kinetic energy operator, and this is Ck sigma dagger Ck sigma. So look at this is K sigma, this is K sigma. So you are this operator is called, you are annihilating at the K sigma at state and then creating at the K sigma. So this is called a number operator. So if any operator is a number operator is always diagonal. And the coefficient or the matrix element becomes the single particle energy eigenvalue. Okay, so this is basically a free electron gas Hamiltonian, and this is already solved. Anybody who has problem, please tell me now. I am going very slowly, and yeah. So this thing, if you don't understand, you will have problems. Yeah. So किसी को कुछ problem है तो मुझे बताओ. Have you studied tight binding model?
Yes, sir.
So it's something like this I and J are something like similar to, I am not saying exactly, but it's something like tight binding. But then in the second quantized version, this looks beautiful. I mean, if you know the basis, and because we have a plane wave basis, I can do this. So there is no problem. And your kinetic energy looks very simple, diagonal, solve. See, if I say kinetic energy and write down this, then you already see that this is written in a plane wave basis with your k state is basically a plane wave state and epsilon k is the eigenvalue. So इसमें किसी को कुछ प्रॉब्लम है तो I can help you in answer it. Yeah, and this is the first thing one has to do. So no problem. So shall I move ahead? Now let's go. Yeah. किसी को कुछ बोलना है? Yeah.
Sir, what do you say about the spin operator? It is just
no. I'm saying this spin operator here. Spin operator तो नहीं है. It's the spin basis है, because this is supposed to be star. I have written there, but it's just a spin basis. So just the way here, this integral is delta function. So your spin chi dagger chi or chi star chi is also a delta function. Yeah, and I'm saying at the free electron gas, your spin degrees are frozen. They are not doing anything because your single particle energy eigenvalue is independent of spin. Because this is just p square by twice m. No? देखो यहाँ your epsilon k single particle energy. This is true for upspin and this is true for downspin. This is the same thing for upspin and downspin. So this doesn't carry any spin index. There is no dynamics because your kinetic energy is independent of spin. That's how I said every single particle state is doubly degenerate. Actually वहां दो लेवल है, बट वो दोनों का एनर्जी एक ही है, इसीलिए एक ही लेवल दिखता है. And if I want to see that, I have to put a Zeeman field. Unless and otherwise I put a Zeeman field, I can't see those splitting. तो आपका सिंगल पार्टिकल एनर्जी लेवल्स में डिजेनरेसी है, डबली डिजेनरेट है, स्पिन डिजेनरेसी है. But you don't see that because your kinetic energy doesn't have a spin. Do you understand?
Yes, sir.
Okay. और कुछ पूछना है तो पूछो. So let's move on. So the kinetic energy, we know we have a platform where we can write down a Hamiltonian for free electrons and number of electrons, which form solids. And two-body Coulomb potential. Can we write down in this language? If we can do it, it is very good. So this also I have written down. Earlier case, there are 4 basis sets I have to take. This is something like I, J, K, L. And then potential energy operator. And potential energy operator is this. This is an operator, by the way, in quantum mechanics of many body theory. Okay, so now let's first calculate the matrix element. Then we'll see. Because if I write down this in a second quantized version, I can go back and show you a little bit so that you become happy. See, potential energy. So this is what we had. And I ended up with 4 sum and half, and then 4 fermion operator, 2 daggers, 2 undaggers, and the potential energy operator matrix element in IJKL basis. So this is what we have to now evaluate. Because this IJKL basis, this is K1 sigma 1, K2 sigma 2, K3 sigma 3, K4 sigma 4. Okay, so that's what we have to do. And so because all are plane wave, we can try looking at it. This is going to be not very bad, I would say. So, okay, so I have written down the matrix element. And you go on putting term. Now, plane wave basis, I put it here. Dagger has there are minus signs, there are 2 spin bases. And then, of course, you have this potential energy operator, half p square, I filtered it out. And then K3, K4, okay, we have. And now I'll try to simplify this. Simplification I have tried here. Okay, and sigmas, basically 2 sigmas, I can pair it a 1 dagger, 1 on dagger, sigma 1, sigma 3, and sigma 2, sigma 4. So there will be 2 delta function in the sigma sector, spin sector, and the orbital part, I had to put it in a proper way by looking at this term, R1, R2. So R1 minus R2, I'll put it like a Y, and then R2 I can put it R, so that I can simplify this and do the integral. It came out to be something like this, and this integral I can do it because see, देखो यहाँ dot है, and if you have dot, then if you take it away, then there will be this magnitude, and cos theta. So there will be angular integral as well, and the angular integral is going to bring out a factor of 4 pi, and this K3 K1 and K1 K3 square plus mu square. So the integral or the matrix element is going to come out to be 2 delta function in the spin sector and 1 delta function in the orbital sector, that is k1 plus k2 equal to k3 plus k4. And then, of course, there's something called E square by 2b, charge and volume. And then I can put it in a proper language. E square by 2b, sum over 4 wave vector, 4 spin, and then this delta function in spin, delta function in orbital, 4 pi by whatever. And then, actually, this you write it C K1 sigma 1, C K2 sigma 2, C K4 sigma 4, C K3 sigma 3. Okay. So actually here I think I wrote down A, but to be proper, I think I had to write down C. So these are all C's, by the way. Okay. So now my Hamiltonian looks like I have bosonic part and electron boson part. I have a constant term. I have a free electron. And then I have a Coulomb repulsion to body. Okay. So the whole Hamiltonian now is reduced to this. This looks a little nicer. We can make it more beautiful. Change the variables. Because, see, I'll tell you here one interesting thing. This delta function says something. This says because these two particles are interacting and your initial momenta and final momenta are the same. So this is something like a momentum conservation. So this delta function ensures not momentum. I have to multiply h cross. So wave vector conservation. So if you change the variable to k1 equal to k plus q and k3 equal to k, because you have momentum, see, because this is the two-body interaction, there has to be something like a momentum transfer or wave vector transfer. So we have to figure it out in writing it in a proper way. So change the variables. I did it like this, k1 and k2 and k3 and k4. So that your k1 plus k2 equal to k3 plus k4. And see, it is k1 plus k2. Your q will cancel, k plus k prime. And k3, k4 equal to k plus k prime. Very good. So this is going to be satisfied if I take this combination. And then in the process, h cross k1 minus k3, k1 minus k3 is this k will cancel, and this is going to be h cross q, that's a momentum transfer. So if you have a two-body scattering, and if you have a potential like this, something like this, then there's a momentum transfer. Okay, and that could be very clear from here. So you can write down potential energy in this language 4 pi by q square plus mu square, and this is what it is, k plus q dagger, k prime minus q dagger with sigma prime. This is sigma, and this is k prime sigma prime and k sigma. And your wave vector indices, so because two delta function in spin will eat up two delta functions, so they are gone, remaining two spin sum, and 4 k sum, 3 are going to be remaining, 1 is going to take out by this delta function. So this is what your two-body Coulomb potential term is in a second quantized version. Now here, so because k, there's a q sum, q is a momentum transfer. So one can separate out q equal to 0 because this is the static part, not static part, q equal to 0 part and q non-zero part. So if we do this, then I put a prime, which is q non-zero, and q0 is just this. And there are names, Hartree and Fogg term. And equal Q equal to 0 term I can think of because there is no momentum transfer. So I can think of this writing in a classical way, meaning I can write it in a, sorry. Sorry. Yeah. So this I can write it in a, I can change a little bit here. I can change K, I can bring it this side and C dagger this side so that I can write like this with a anti-commutation relation. So this will give you term like this. And one is dealing with fixed n can be replaced by its eigenvalue. So your first term cancels with the constant term in h. This is going to cancel. And the remaining is only this, e square minus e square by 2b, 4 pi by mu square n by v. And this is going to be 0 in proper thermodynamic limit. That is, you first take L goes to infinity and then take mu goes to 0. So after doing this, you will end up with a pure electronic Hamiltonian because your bosonic terms are also cancelled with the part of Hartree. And a part of Hartree term, Q equal to 0 process, is going to be 0 in proper thermodynamic limit. After doing all this, you will end up with a term where you have a pure electronic Hamiltonian where you have a kinetic energy, and here you have a Coulomb potential with Q non-zero. See, this prime is Q non-zero. Q0 we have already done it. And mu I can put it 0 now so that you can have 4 pi by Q square. So mu is just a term which helps mathematically at this moment. And then you have, this is a two-body interaction. And now one has to solve this and get the ground state energy per particle. That's the aim, because this is a exactly solvable problem, which we know in free electron gap. Now, this is an interaction, and solving an interaction term is not very easy. That's very, very difficult. And because this is an n-body problem. So we'll think of solving this in some way to calculate the ground state energy. Okay. Actually, how are you going to solve this? There are many ways. You can have perturbative way, you can have variational way, you can have non-perturbative. There are varieties. But here, if you want to solve it, variational calculation for single particle is fine. But for n particle, it is very difficult to crack down a n particle wave function. Not very easy. Non-perturbative approaches are also not, you can't apply just now here. I'll tell you what are the non-perturbative approaches. Here, the best thing we can try doing is a perturbative method. Meaning, perturbative method कैसे काम करता है मालूम है? Anybody who knows how a perturbative approaches work? आपका quantum mechanics में when do you do a perturbation theory?
So in first sem.
No, but I'm saying, suppose I'll give you a problem. How do you know whether a perturbation theory can be done with this problem or it cannot be done? तो आपको कोई idea है कि in which way you do perturbation theory? You must be knowing about the problem. What is the essential features where you can do a perturbation theory?
So disturbance should be very small.
No, I have already given you an answer here. If you want to have a perturbative approach, you need a small parameter, because your the term which you are going to treat perturbatively, that should contain a small parameter. Otherwise, you just can't do a perturbation. because perturbation में see, this is a exactly solvable problem. We know it, but in order to solve this, you need to have a small parameter, because these are operators. This is 4 pi by q square, q dependent potential. This is a volume, this is charge. तो यहाँ small parameter नाम की चीजें मुझे कोई दिखता नहीं. So if you want to do perturbation theory, first of all, you have to dig out a small parameter if at all it exists. So you have to write down the Hamiltonian in a proper way. देखो, your theories problems becomes very hard. Because यहाँ one cannot see, one is not able to see a parameter here. So I have to put this Hamiltonian in such a way that the parameter should come in. And then if I see that parameter, whether it is small, then I can do a perturbation theory. If it is not, my perturbative result nobody is going to believe. Okay, so this thing we have to learn properly. अब देखो, जो क्वांटम मैकेनिक्स में पढ़ाया जाता है, those are very simple by the way. One doesn't verify. वो रियलिस्टिक थर्मोडायनेमिक सिस्टम नहीं पढ़ाया जाता, because one is interested academically for some single particle problem also. But here we are dealing with a system. So you have to really see if there is something very small as a parameter in the problem through which I can expand. And then I can look at either the first order or second order, or whatever order I can go. Maximum first or second, not beyond. Because it's very hard to do anything beyond. So I'll stop here, or we should go more, because tomorrow I won't be able to take the class again, because I have some meeting there. So I don't know. This is going to happen to me on and off. Yeah, कोई प्रॉब्लम है तो मुझे बताओ अभी. Yeah. So समझ में आ रहा है, समझ में नहीं आ रहा है. See, I don't know. So these things are going to be little new to you, but then the actual system, which is basically a way you can do is statistical mechanics, and that's going to be a little tougher, I would say. But then one has to understand, and it's not that people don't know this. I mean, if you try putting a little bit effort, you will understand most of it. Yeah. And you will be able to do calculations also. Yeah. So if you have problems, please let me know so that I can try making it easier and easier for you. Yes. Bolo. Any question, any suggestion, any queries, anything?
सर ऊपर जहाँ पे म्यू टेंस टू 0 किए हैं, वहाँ पे शायद वहाँ एक दो क्वांटिटीज और कुछ अप्रोक्सीमेट किए हैं, वो समझा दीजिए पर.
हाँ नहीं, यहाँ मैंने जैसे see whenever I did this Coulomb potential part, तो यहाँ there's a factor of q square plus mu square at the denominator, 4 pi by. So what I said was, we have a piece here which is there after summing over the bosonic term. Just look at this. Okay, this. Right? Now this part, so after you did the integration of bosons and boson electron interaction and then summing it, you end up with this. And then your electronic part में ये है. So then what I did was, I changed the variable of this, and then I wrote down properly, and then I took the q equal to 0 part. And q equal to 0 part का एक term इससे cancel हो जाता है. That is n square minus n है वहाँ. I'll show you. So see, this n square, e square by 2 n square by v 4 pi by mu square. This term is going to get cancelled with that earlier bosonic term. And then the left out is e square by 2v 4 pi by mu square n. अब ए n को मैं अभी ऑपरेटर नहीं n का आइगन वैल्यू लूंगा स्मॉल n डेंसिटी n by v. Yeah, you can just take it n classical. So your n by v. Oh, that's what it is. With the minus sign, e square by 2 n by v 4 pi by mu square. So this is for q equal to 0. So q equal to 0 का Hartree का एक term, it cancels with the bosonic term and the one term remains, and this remaining term I'm saying you can take a proper thermodynamic limit where L goes to infinity first. Yeah. And then take mu goes to 0 and 1 by mu is much less than L. In this limit, this term goes to 0. So then you will have your bosonic part is gone, Hartree ka bhi this part is gone. So you will have only this Hamiltonian now, a pure electronic kinetic energy, and then the Coulomb potential, two body, with q not equal to 0. A prime का मतलब है q not equal to 0. Q equal to 0 term we have already taken away. One part of that cancels with bosons and another part goes to 0 in the proper thermodynamic limit. And then we switch off mu, because once I have q non-zero, I can switch off mu. देखो q 0 रहेगा तो I can't switch off mu, because then q equal to 0 is going to be making problems, because it will be infinite. I don't want those. So first take the q equal to 0 term and it will remove all the on-physical natures, and then this is what it is. So now you have to solve free electron kinetic energy plus 2 body Coulomb potential for n particle problem with wave vector transfer non-zero. And interested in ground state energy per particle, because we can be interested in many things. So don't go here and there. So let's focus on this. So मैं कह रहा हूँ इसको solve कैसे करोगे? And one method I am saying, because variational and non-perturbative I throw it away, and I said let's think of perturbative method. But perturbative method में you have to have a small parameter here, and by looking at the Hamiltonian, I don't see any small parameter. So now you have to relook at this problem in a different way and parameterize this fellows such that we can see a small parameter. And we will do it. I mean, don't worry, because that's a way theorists look at the problem. Yeah.
सर कैपिटल पोटेंशियल की लेंथ है ना?
कौन कैपिटल V?
कैपिटल L टेंड्स टू इंफिनिटी जहाँ की.
No, capital L is see, this V is volume. Volume is L cube. L is the size of the box.
Yes.
आपने free electron gas जो solve किया है, you put an electron in a box, and box has this your cube. Cube has a length L, and L cube is V. So this V has L cube. Sorry. Yeah. ये जो V दिख रहे हैं ना? Yeah. Yeah. और कोई problem? So the next lecture we'll see how we are going to parameterize the kinetic energy and potential energy that's given. So these are very interesting, by the way. You will look at this. This is just to parameterizing and looking for a small parameter. Once we have this, then we can start looking at the Yeah, I'll go over to other parts sometime, but अभी ज़्यादा हो जाएगा. I don't want to do it. I mean, if you're interested, I can go for hours, by the way. I have no problem. But we'll go slowly for beginning so that you can get into the ideas of doing condensed matter. Yes. आपने क्वांटम फील्ड थ्योरी में कुछ कैलकुलेशन वगैरह करे हो या नहीं करे हो? I mean, something creation annihilation operator operating on some vacuum state and getting some answer. ऐसे कुछ किया गया है या नहीं? Yes, no. And also you need a bit of statistical mechanics, because see, this is purely quantum statistical mechanics. Yeah. और कुछ बोलना है तो बताओ. या और किसी को समझ में नहीं आता है तो प्लीज फील फ्री टू टॉक टू मी, because online classes I can't make out things, so I can only make out things are how much you interact with me. So बंद करें यहाँ?
Yes, sir.
So tomorrow I may not be able to take the class. Let's see if I will, then I'll again write you in WhatsApp group. Okay.